All set? Here we go. Today's session is going to be all about discussing problems that have appeared in Indian universities in the last decade or so. This is going to be very important for you if you happen to be a first engineering student and if you have this course of engineering mechanics. So, welcome to the world of statics. And today we'll be discussing problems based on general case of forces in a plane. So, good evening, everyone. This is Manas Patnaik, your friend and tutor. And first of all, at the outset, let me tell you the problems that we had been discussing till now, all of them were coplanar. Yes, sir. We saw all the forces were coplanar. Secondly, all the forces were concurrent as well. And we have used this technique of Lami's theorem because in most of the cases we saw that there were only three forces. All of them were passing through one single point and they were coplanar. Okay, now this Lami's theorem works wonders for us. But what if the forces are coplanar but they are not concurrent? That means the forces happen to be non-concurrent. And let me tell you, there is a wonderful technique called the equations of equilibrium where you can simply apply summation fx, summation fy and summation of moment of all the forces equal to 0. If you are ever stuck in a problem of statics, this technique, these equations of equilibrium are going to get you out of trouble always. Yes, it might involve a lot of steps as you have to make equations, solve them to get to the unknown value of forces, but this technique always works. Okay, because when you talk about Lami's theorem, there is a constraint that you can only work with three forces, three concurrent forces. Okay, if you've got more than three concurrent forces, you've got to use this, and you can use this anywhere, anytime you want. Fx0, Fy0 and moment 0. So it is my responsibility today to explain you and demonstrate you how all of these things can be applied in the best possible way. What you need to know is how to create a free body diagrams, and even that I'll be explaining you in detail. So here we go with problem number 1. Watch this. This is going to be interesting. Take a look. Find the angle theta for which the bar shown below maintains equilibrium. And one sec, let me just show you the problems that we'll be discussing in today's session. This is problem number 1. Then we'll be discussing this problem over here. Take a look. Okay. Very interesting. And then we are going to take a look at this problem. All of these problems are such that we'll be applying the equations of equilibrium and we'll be trying to work out the value of unknown forces such as tension in this case. So watch this video right till the end. This is going to be very, very interesting. Okay, let me start with problem number 1. Take a look. Find the angle theta for which the bar shown below maintains equilibrium. Assume the length of the bar is 12 and weight is negligible. There is no weight. The length of the bar is 12. And if I can just zoom in, all of these segments of the bar, like AC, its dimension has been given, its length has been given to us. CD is 3, DB happens to be 4. So all the dimensions have been given. Even this inclined surface over here, the angle of the incline is something that you can work out, okay, with the help of this triangle. So tan theta is equal to 3/4. Just do the inverse, you'll get the angle. It's very, very simple. Now let me start by making the free body diagram. Here it is. Okay, these are all my reference lines. Okay, nothing fancy. The first thing, students, that you can do, you can simply take a look at this triangle. If I say that this angle is theta, let me zoom in again. If this angle is theta, so tan theta will be equal to 3/4. That means theta will be tan inverse 3/4. And the value of theta you will get over here is this much, 36.87. What? Theta equals tan inverse 3/4. Done. This is the result that I have written. Okay, if this angle is theta, then this angle also is going to be theta. Now you know the math. Secondly, there is this 200 Newton force over here. Then you've got 100 Newton force horizontal towards the left hand side over here. Done. All forces? No. If you remove these supports, then only you are making the free body diagram. So perpendicular or normal to the surface, you'll have a reaction at A. Normal to the surface, you'll have a reaction at P this way. Okay, so if it is making an angle of 36 degrees approximately over here, then if this happens to be the normal, and if this is the vertical, the angle between normal and vertical will also be 36 degrees, 36.87 to be very precise. Simple concepts that we had discussed in the previous session. Okay, watch this. This is going to be very, very interesting. Now comes the point where I'll be simply resolving the force of RB into components. So if you watch, we zoom in slightly. If you watch, this RB can be resolved into RB cos 36.87 and RB sine 36.87, isn't it? Yes, sir, we can do that. So do it. Here we go. RB cos and RB sine. Done. Now comes the time where we'll be applying the equations of equilibrium. You can apply the equations of equilibrium anytime. Okay. Fx0, Fy0, moment 0. Right? So if you are slightly not confident with Lami's theorem, go ahead and use this technique. This is going to be very helpful. Now let's start with summation Fx0. So sir, there is this Ra which is to the right. So take it as positive. Okay, sir. 100 is to the left. Take it as negative. Okay, sir. RB sine 36.87. This is also to the left, sir. So take it as negative again. Okay. So let me write them. Plus Ra minus 100 minus RB sine 36.87. So this is our equation number 1. Okay. And you can see that there is one equation and two unknowns. Ra and RB are the unknowns. We cannot proceed. Now let's apply another equation. This is summation Fy equals to 0. If you watch carefully, this 200 Newton is downwards, negative. This is upwards, positive. These are the only two forces in the y direction. One of them is positive while the other is negative. You simply write negative 200 plus RB cos 36.87. Done. Solve for RB. This is what you get. Very simple. And once you have the value of RB as 250, you can put it over here and get the value of Ra. Simple math. Now, so what shall we do? Now you should go for another last moment equation or equation of equilibrium called the moment equation equal to 0. Now, which point shall I take the moment? Should I choose A? Should I choose C? Should I choose D or B? First of all, let me start with point A. If you take the moment about point A, you don't have to worry about Ra because Ra is actually passing through A, and hence you cannot drop a perpendicular around it. Its moment is going to be 0. When you take the moment about A, you have to deal with 1, 2, 3 and 4 forces. Okay. When you take the moment about A, you have to deal with 4 forces. Right. This is a small practice that you should always do before choosing the point for moment. Okay, so A has got 4. If you choose the moment about C, again 200 Newton forces out of the picture, you have to deal with 1, 2, 3 and 4. So one more, C also has 4 forces. What about D? If you talk about D, again you have Ra and 200. This 100 Newton force is out of the picture, but you have Ra 200. You also have RB cos. You also have RB sine. Again, D also falls in the same category where you have to deal with as many as 4 forces. Okay, but when you take the moment about B, these 2 forces are out of the picture because they pass through B. You can't drop perpendicular on them, therefore their moments are 0. And here you are left with only 3 forces, 100, 200 and this Ra. So the best option that we have is point B, and we are going to take the moment about point B equal to 0. How to take the moments? This is something I have found students confused. Okay, so whenever you want to take the moment, you always should draw the line of action of the force and then drop the perpendicular from the respective point. The point in this case is point B. Let's say we want to take the moment. We want to take the moment of 100 Newton force. Just watch. Sir, we want to take the moment of 100 Newton force. So, sir, this is going to be the line of action of 100 Newton force. From where are you taking the moment? Sir, we are taking the moment about point B. Watch this. This is very interesting. So drop a perpendicular from B. This is the perpendicular. So you know this force. This force is 100. What about this perpendicular distance? Do you know this distance? So we still don't know the distance, but we can work it out. Yes, you can work it out. So that's the first thing. Okay. Secondly, let me erase this. What about this 200 Newton force? So this is the force. Can you drop? This is the line of action of 200 Newton force. We are taking moment about B. This is going to be the perpendicular distance. It is this distance that you now need to calculate. Okay. And finally, there is one more force, that is this RA. This is the line of action of RA and perpendicular drop from B. This is the perpendicular distance. How much is this distance? Well, all of these distances can be calculated. You don't have to worry. I'll demonstrate it to you. Watch. A very interesting case indeed. Take a look. Let me zoom in. And what color shall I use? Just a second. Orange. Take a look at this triangle. It is a right angle triangle. Yes, sir. Agreed? Yes, sir. In this right angle triangle, we know this theta. Okay. We don't know this theta. It is this theta that we are actually calculating, right? Anyways, let me go ahead. What is this distance? Sir, this is dB. What is the length? Sir, this is 4. If this is 4 and this is theta, this is going to be 4 cos theta. This is going to be 4 sin theta, right? The side in front of the angle is sine component. Along it is the cos component. Again, this is 4, which is the hypotenuse, and this is 4 cos theta. This is 4 sin theta. We need this distance so that 100 multiplied by this perpendicular distance will give you the moment of this force. Okay. So this is going to be 4 sin theta. That's done, sir. Okay. The second distance that I am really interested in is this one. This is the force. Watch. Force, and this is going to be the perpendicular distance. Sir, how can we work this out? Let me just demonstrate. Take a look at this triangle and then I'll zoom in. Okay. We just want to calculate theta for equilibrium conditions, just to ensure that the bar AB stays in rest. Take a look now. Oh, why did I erase? I had to zoom in. Take a look. So from C to B, that means 3 plus 4. This hypotenuse is 7. If this is 7 and this is theta, then this has got to be 7 cos theta and this has got to be 7 sin theta. Done, sir. Mark it. This is 7 cos theta. I'm marking the perpendicular distances for the forces. First of all, I did for 100, which was 4 sin theta. Now I have done for 200, which is 7 cosine theta. And finally, I have to deal with this RA. If this is the force RA, then the perpendicular drop from B is there. Okay. And let me make this triangle. This is the perpendicular distance. This is the perpendicular distance, right? Let us now take a look at this triangle. Watch. So this is theta. Yes, sir. Agreed. How much is this? So 5 plus 3 plus 4. How much? 12. So if this is 12, this is theta. This is going to be 12 sin theta. This is 12 cos theta. Okay. And you need this 12 sin theta. Done. So forces and the corresponding perpendicular distances with respect to point B have been worked out. Now you simply need to write the moment equation. This is going to be fun. Watch. Let me choose first of all 200. Yes, sir. 200 multiplied by what? No, I have chosen 100. Okay. Whichever order you go, don't worry. This is the 100 Newton force. Yes, sir. This is the perpendicular distance. So basically what you have is 100 multiplied by 4 sin theta. Anti-clockwise with respect to point B. So positive sign. 100 into 4 sin theta. Okay, sir. Now you have another force of 200 Newton. So this 200 Newton force, and this is the perpendicular dropped. Okay, so 200 multiplied by 7 cos theta. Again, anti-clockwise, positive. Done. Very easy. Finally, you've got this RA. So this RA multiplied by the perpendicular distance again, this is 12 sin theta. So clockwise, therefore negative. And RA's value we know is 250. We have got it, right, from the previous equilibrium condition. Now, students, what you need to do is you need to have all the sin thetas on one side of the equal to sign, while cos thetas on the other side. This is how you need to make the arrangement. And just take cos theta over here, 2600 over here. So you'll have an equation in tan theta, which is going to be equal to 7 over 13 go for the inverse, go for the kill, and this is what you get. So if you keep this bar at an angle of 28.3 degrees, where 200 Newton force, 300 Newton force, and there are these supports, one of which is absolutely vertical while the other is inclined. Okay, if you keep this bar at this very angle, it is going to stay in equilibrium forever. Right? I just hope that you've got this entire problems and its explanation. Okay, now moving on to the next problem. So take a look. We have some water. The weight of the prismatic bar, this green colored bar over here, is a prismatic bar. The weight is given as 3 kilonewton. The length is L. Determine reaction at the hinge and tension in the cable. For this very question, I'll be showing you two approaches. One approach is something that you can apply everywhere. That means equations of equilibrium. Fx, Fy and moment equal to 0 for all the forces. This is going to be our first approach. In the second approach, I'll be talking about Lami's theorem, how you can apply Lami's theorem, right? Because whenever I see three forces, I always try to check whether we can apply Lami's theorem or not. And since the body is in equilibrium and three forces are acting on it, then all of those forces, their lines of action of all of those forces must pass through a common point. And this is the logic that through which I'll be explaining you the second approach. But wait, first of all, it's going to be, we are going to keep it very simple. Let's apply the equations of equilibrium. Free body diagram of what? Sir, only prismatic bar. So free this prismatic bar from this cable and from this vertical wall and from this support also. Okay. And if you remove this hinged support, you have to make a horizontal and vertical component. And by the way, the weight of the prismatic bar is going given. Where are you going to put this weight? Sir, we are going to put the weight right at the center. Right at the center. Weight acts at the center. And this distance over here to the left of the center is L by 2. And to the right of the center, again, the distance is L by 2. Because the length of the bar happens to be L simply. Right? And this is exactly what I'll do. Here it is. Secondly, sir, when you remove this support, hinged support, it has to be replaced with appropriate reactions, horizontal and vertical at A, AX, AY. Done, sir. And thirdly, you have this tension, making an angle of 30 degree with this bar. So here we'll have the tension. Here it is. Okay, and this angle also has been given to us, by the way. This is 60 degree with the vertical. If this is 60, then students, you know what? This is 90. This is 90, 60 is 150. And this has to be 30. So this is 30. That is why I've written 30 over here. Simple math. I'm sure you can work it out. Okay. Now now start by applying the equilibrium condition. I'll be taking moment about A, because when I take the moment about A, these two forces are out of the picture and I am only left with this 3 kilonewton force and this tension T. Now to take the moments, the best approach is to resolve T into components. Let me demonstrate. If you want to resolve T into components, this is how you need to do it. This is the cos component of T. Let me just write T C30, and this over here is going to be the sine component of the tension. So let me just write T S. Oh, just a second. This is, did I do something wrong? This T is making an angle of 60 degrees. This is 60 degrees, by the way, with the horizontal. If this is 60 degrees, this has got to be a T cos 60. Let me make this correction. And this is T sine 60. Okay. If you took this angle, then this would have been T cos 30 and this would have been T sine 30. That would have also been correct. No issues. Right? Okay, sir. Let's apply the moment equation. So where shall I start? Let me start with T cos 60. So if you watch, this is the line of action of T cos 60 and this is the perpendicular drop from A. Can you tell how much this perpendicular distance is? Yes, sir, that's very easy. If you watch carefully, this triangle AB, and what the hell is this point? Let me make it as O. Okay. So if you zoom into this triangle, right angle triangle AOB, this is the hypotenuse, which is L. This is L. How much is this angle? Sir, this angle is 30 degrees. So this is going to be L cos 30 and this is going to be L sin 30. Understood? Okay. So T cos 60 into L sin 30. Can I do this? L sin 30. Secondly, sir, you've got this component of T sin 60 and you want to take its, this is the line of action of the force. This is the line of action of T sin 60. And if I can just drop a perpendicular, this is going to be that perpendicular. And this is O. Let's say this is M. Okay. Let me write M somewhere else. Otherwise. Okay, so now if you watch, take a look. So what is this angle? Sir, this angle is 30 degrees. Agreed. So if this is 30, this also has got to be 30. So I can write 30 degrees over here. So if this is 30, watch. L, this is going to be L cos 30 and this is going to be L sin 30. It is this L cos 30 that we are interested in. Okay. L cos 30. Now watch. Let me zoom in again. So about point A, here it is. T sin 60 multiplied by perpendicular distance from A. T sin 60 multiplied by L cos 30. This is what you need to do. So it is anti-clockwise and that's why positive. Okay, you can see this. Now we are only left with this 3 kilonewton force and this is also fairly simple. Watch, this is the line of action, okay, of 3 kilonewton force. Let me make this a bit more clearly. And this is the perpendicular drop from A. Okay, this is O, M, and let's say this is N. Simply. Now take a look at this triangle. Which triangles are? Triangle AGN. Can you see this? Triangle AGN. In this triangle, you've got this hypotenuse as L by 2. If this is L by 2, this is going to be L by 2 cos 30. This is going to be L by 2 sin 30. Very, very simple. Okay, we are taking moments about A. So what you really need is this one. This is the force and this is the perpendicular distance. This is going to be L by 2 cos 30. Let me write this. This is L by 2 cos 30. So it's very simple. 3 kilonewton force multiplied by perpendicular distance. Let me zoom in. 3 kilonewton force. This 3 kilonewton force multiplied by this perpendicular distance, that is L by 2 cos 30, and here it is. Okay, very simple clockwise. That's why a negative sign. Now you can cancel the L's one at a time. Okay. And what you're left with is this tension. Now, if you can take T as common, you see sin 60 cos 30 minus cos 60 sin 30. Let me take T as common and shift this to the right. So 3 by 2 cos 30. You've seen this before. Sin A cos B minus cos A sin B. Sin of A minus B. Sin of A minus B. When you do that, what you have is simply this. Right? And this is going to be sin 30. Now you can simply plug in the value of sin 30 and cos 30 and solve for T. What you get is 2.6 kilonewtons. So yes, the approach seems a bit too long, but once you have framed the moment equation, it is just about mathematics. Okay. So that's how you can calculate tension T. Now you can also go ahead and calculate the value of the reaction, the overall reaction at A. Let me just briefly explain you this. Summation Fx0. Now you have to deal with Ax positive and T cos 60 negative. Any other force? No, sir. So simply write plus Ax minus T cos 60. Okay. And solve for Ax. You already have the value of T. T is 2.6. Keep it over here. Solve for Ax. Okay, sir. Then you've got summation Fy equals to 0. So this is upwards, okay, positive. This is downwards, 3 kilonewton negative. And sir, this is upwards, positive again. Plus Ay minus 3 plus T sine 60. Right? Again, put the value of T, 2.6 kilonewton over here, and then simply solve for Ay. What you have is 0.75. So you've got these horizontal and vertical components. If you want to find the net force at A or the resultant at A, what you need to do is use this formula, simple. Root over Ax square plus Ay square. Just plug in the values 1.3 and 0.75. This is what you get. You can even calculate the angle. You can even calculate the angle that the resultant is going to make with the horizontal. All of these things are possible. So this is what our answer is, using the equations of equilibrium. Now, some of you guys must be thinking, so okay, this was approach 1. And as far as we can see that we had to do or deal with a lot of mathematics. If you are someone who does not like math a lot, you can use approach 2, which I'm just about to explain. Okay, let me make the free body once again. Here it is. This 3 kilonewton weight right at the center, and then the tension over here, and the line of action. Please make a note that I am actually making the lines of actions also. And how many forces are acting? So there is this tension T acting. So again, the weight of the bar is also taken into consideration. And so we know that there are going to be one horizontal and one vertical component, but the resultant is going to be there. Okay, the resultant is going to be somewhere along this direction. So the idea is very simple. If there are 3 forces acting on a body and the body is in equilibrium, listen to this. If there are 3 forces acting on a body and the body is in equilibrium, then all of the forces, then the lines of action of all of the forces should pass through a common point. This is the basic philosophy, not a philosophy, but a rule for 3 force equilibrium. If a body is in equilibrium under 3 forces, then all the 3 forces, 1, 2, and the third one through A, must pass through this common point. Let me show this to you in one go. Here it is. All of them have to pass through one common point. Now this is valid for only 3 forces. If there are more than 3 forces, don't even think of applying such a technique. Okay. All right. I saw 3 forces and I thought about using Lami's theorem, but there are a lot of angles and their calculations, and you've got to be good with geometry. Okay, this is something that you've learned at school level. Do you remember isosceles triangle, equilateral triangles? All of those fundas are going to come over here. Watch. Okay, so this is the line of action of T. That's 3 kilonewtons line of action. Then the line of action for the reaction at A has to pass through O. In the previous session, we have seen the components of RA in the form of AX and AY. We actually worked out these components and then we had plugged it into this formula, AX square plus AY square, to get the value of RA. This is what you got, right? Here we are going to do the exact reverse. How do you approach, sir? So this angle 60, can you see this? Yes. Mark it. Just a sec. Okay, sir. This bar makes with the vertical, this is 60 degrees. So bar and vertical, this is 60 degrees. Okay, sir. Now what? So if this is 60, these two lines are parallel. Okay. And this is the transversal. Okay. If this is 60, then sir, this is also 60. Okay. Then mark it. Let me erase 60 and this is 60. So sir, this is a straight line. This is 60. This is 120. Very simple. Okay. If this is 120 and this is 30, 120 plus 30 is 150. Then this has to be 30. Yes, sir. Sum of all the angles is 180 degrees. That's why 30 degrees. If you watch, these two angles are same. Then the sides in front of them will also be same. So if this is L by 2, this also has to be L by 2. Now you know this is L by 2, isn't it? So this side is also L by 2. Now watch. Let me zoom in. Take a look. Since these two angles are same, if this side is L by 2, you can also make a claim that, sir, this also will be L by 2. If this is L by 2 and this is L by 2, you know this, these two sides are same, then the angles in front of them will also be same. If that is the case, you can say, sir, this angle is x and this is x, so we can simply write x plus this 60 degrees will be equal to 180. So this is going to be 2x equals to 120, x equal to 60. That means these two angles will also work out as 60 degrees, isn't it? So we had to go through a lot of calculation, because in order to apply the Lami's theorem, what you need is the force diagram. So you need proper angles, the angles that these forces are making either with the horizontal or with the vertical. And let me put all of these forces in one single picture. Okay, here we go. Let me put this 3 Newton over here, exactly here, 3 kilonewton by the way. Then you've got this tension T. Tension T, as you can see, is making an angle of 60 degree with the horizontal. So you can make it over here, 60 degree with the horizontal, turns up. And this resultant at A, or reaction at A, is making an angle. What is the angle that it makes with the vertical? You can see here, if I can shift this resultant, you can clearly see this angle over here is 60 degrees. So the resultant at A, RA, makes angle of 60 degree with the vertical. So RA makes an angle of 60 degree with the vertical. That is exactly what I've done. Once you've got this diagram ready, you can very easily apply Lami's theorem, okay, which I'm going to, and find the unknowns. So you have unknown in the form of T and RA. Let's go ahead and start with 3 kilonewton. So these are the two forces remaining, and the angle between them, its sine has to be taken. So 3 kilonewton divided by sine of the angle between the remaining two forces. It's very simple. This over here is 30. So 30 plus 60. Let me zoom in. If this is 60, this is 30, isn't it? 30 plus 60. That means 90 degrees, by the way. This is 90 degrees. Secondly, if you pick T as your force, then this is the angle. So this is going to be very simple. Sine of 180 minus 60. Agreed? Yes, sir. And if you take RA, it is this angle that you need to work out. This is going to be simply 90 degrees, 90 plus 60. Done. Solve. This way, solve for RA and T. These are the values that you get. 2.6 kilonewton and 1.5 kilonewton. These are the same answers that we got by applying the equations of equilibrium. T equals 2.6 and R equals 1.5. You can make a check, right? Again, let me have some water. This is going to be very interesting. Okay. And we'll be now discussing our final problem. Oh. What was the problem I thought of discussing? Slide 58. 58. Okay. A very interesting one. All right. So the following arrangement shows a boom AB. Supported by a hinge and a cable. This is a hinge and a cable over here. Calculate the tension in the cable and reaction at the hinge. It is the tension in this cable that we need to work out, and we need to find the reaction at the hinge. Obviously, if you remove this support, you have to replace it with a horizontal and a vertical. That means AY and AX. And it is this resultant, the resultant of AX and AY, that we are very much interested in. Again, all of these things can be worked out. So let us start by making the free body diagram. Free body diagram of what's the boom AB. And here we go. Done. Watch. So a hinge has to be replaced by a horizontal and vertical. Okay. There is this cable over here. We are interested only in this boom AB. So this is the tension. Done. Okay. And some distances have been given to us, and we are going to make very good use of it. Now take a look. You can start with Fx0, Fy0. Better to start with the moment zero equation. Okay. And take a look. This is a triangle. Two sides are given. You can simply apply. You can say theta is tan theta equal to 210 over 150. That is exactly what I've done. And I've got the value of theta as 54.46. Done, sir. apply the moment equation. If you take the moment about A equal to 0, you have only two forces, 540 and T. T is unknown, that will be worked out. Take the moment about A equal to 0. Now T can be resolved into components, students. How? Let me just show this to you. T is going to have two components. One over here. Sir, what is this component? This is going to be T cos 54. Okay. And another component is going to be over here. This is going to be T sine 54.46. Okay. Okay. Just take a look. Now AX and AY pass through point A. No moments, zero moment. Even T sine 54 passes through A. Again, its moment also will be 0. So you are now left with T cos 54 multiplied by perpendicular from A. So if you watch this T cos 54, let me zoom in. This is the force T cos 54 and this is the perpendicular distance AB. So AB is actually equal to 210 mm. Do the math, anti-clockwise, positive. Okay, so I've gone for 540 first. Let me explain you this. Let me show you T cos 54 multiplied by this. Done. And how does this come into the picture at 540? Watch. Force is 540. If you drop a perpendicular through A, this is the perpendicular and this is the distance 150. So 540 multiplied by 150 is very simple. And then you had this T cos 54 multiplied by this distance, which is 210. So one is clock, one is anti-clock. And if you solve this, the value of T which you get is 663.57. I hope this is very simple to you, right? Second thing that we'll do is summation of fx0. Now you have to choose positive, negative. Is there any other force in the horizontal direction? I don't think so. Plus AX minus T sine 54.46. Simply put the value of T as 663 over here. Get the value of AX. Summation Fy0. Positive, negative, positive. Plus AY minus 540 minus plus T cos 54.46. Put the value of T as 663 over here and then solve for AY. This is what you get. Once you've got the value of AX and AY, you can also find RA. Okay, you know this technique, right? It's very, very simple. So we've got everything. We've got the tension, we have got the reaction. So it was fun, right? So students, yes, that was all from my side for today. And if you want to learn engineering mechanics in a very comprehensive manner, enroll in my course as soon as possible. Link is in the description, and I'll be discussing in my application all the chapters in very, very detail, right? It's going to be fun. So do have a look. Thank you very much. Good day. Take care.